project by Quinn and Diego Rodriguez. We're going to be documenting the design and testing process for our schematic and our PCB for an audio activated LED. Our motivation for this project, we knew from the start that we wanted to use an audio sensor, so we decided to make a mini iteration of an audio activated lamp using a microphone along with a series of amplifiers that drive an LED. The applications of this project are widespread. They can be applied to any circuits that utilize op amps and many audio applications. Our design overview is decently simple. We have a small electric microphone that feeds its input signal into a preamp, which is just a non-inverting amplifier. This signal then goes into a full wave rectifier so we can get a steady DC value, which then goes into a comparator op amp, and where we have a threshold. If this voltage surpasses this threshold, it should drive an LED.
This is the schematic for our PCB. This right here is going to be the preamp, right? And this is the microphone that gets fed in to the preamp. These two resistors right here just uses voltage division to cut the supply voltage to the microphone in half, and gets fed into the preamp. Now it gets fed out at 10 times the input, and the reason we chose that is because whenever there's a voltage change in the microphone from when you speak into it, it's really small. So we decided to amplify it so that the comparator op amp would eventually be able to detect it. This is our full wave rectifier here, which converts it to a DC signal, meaning that which means that the input signal gets transferred above the the reference voltage that we decided to be 6 volts, which is half of the supply voltage to each op amp. So once it gets shifted above that reference voltage, it's now essentially a DC supply. And once it leaves the full wave rectifier, it's just getting compared to a threshold voltage that we set that we're going to describe later. And once it surpasses that voltage, it drives the LED high or low, meaning that it's turned on or off.
Here's the PCB layout that I created. You can see the top view and the bottom view. This was definitely a very interesting process, as it's unlike anything we've done before, and it's much more complicated than the simple layout that was in Lab 2. Initially, the first iteration I created was about less than an inch long, and the second one was far too large compared to the maximum 100 by 100, but we eventually got down to this design. Now for our demo video, here's our breadboard working.
So this is the microphone, and then this is the IC, and then this is our LED. Alright, and then just any sort of tapping.
I think we can. No.
So here's our simulation results versus the real world results. For reference, the real world results that we used on our PCB was using a sine wave input instead of the actual microphone. And the reason we chose that is just to be consistent with the simulation that we used on KeyCAD. So you can see here that our inputs here is 500 millivolts, and our expected output was a 5.5 volt average. Now, our output in the real world was only 4.5 volts. That was the average. And we think that's just because of man-made errors such as the resistor values and the op amp. Here's our simulation and real world results to the full wave rectifier. You can see this green line here is the output. See that it's all above this 6.0 reference voltage, which is essentially a DC voltage. You can see in this graph right here, this is our input voltage, which is 4.5 volts, and our output here being 7.4 volts. Now, the output voltage was a little bit higher than we were expecting. However, the minimum voltage is still above that reference voltage that we had set to 6 volts,
As long as it.
which essentially means that it's also a DC voltage. So the full wave rectifier still did its job. And finally, here's the results for the comparator op amp. You can see this green line here is the input, and this yellow line is the output, driving high when it crosses that threshold voltage of 6.5 volts, which we set to be right above this line right here. You see it drives high when it's above that, and it drives low when it's beneath that reference voltage. In this graph right here, you can see our input voltage to the comparator, which is 7.4 volts. And you can see the output driving high and low depending on the reference voltage. Now we had to change the reference voltage to 7 volts because the 6.5 volts would have been too small for us to detect an LED turning off. So we just had to raise the reference voltage a little bit. And once we did that, you could see the LED clearly turning on and off. And here's just a table of our results and measurements to put it into better view. You can see that our expected output is different than the measured output. And despite the measured output from the preamp being lower than we were expecting, the measured output value of the full wave rectifier was actually a little bit higher, which meant that we had to change our threshold voltage a little bit. And our expected output value for the comparator is a little bit different, but that's just because in the simulation, we didn't connect the output of the comparator op amp to an LED, but they both had the same form, and the LED was still turning on and off.
We learned a lot of valuable lessons. One of the big ones is very closely reading the data sheet. The data sheet for the microphone that we ordered actually had a small circuit that we didn't notice. And we also noticed that if the input voltage was, our input voltage that we put into the microphone was too large, and if we read the data sheet better, we wouldn't have had this problem. Another lesson is just testing our project further in the development stage. We could have avoided a lot of issues. If we had access to a microphone, we could have gotten a lot better insight into setting the voltage threshold correctly. And with these fixes, our PCB probably would have worked perfectly. This project really allowed us to utilize our skills, and for the first time in the EECE program, we created something by ourselves without direct instruction or guidance. With only a short crash course on the basics of KeyCAD, we managed to apply the information that we learned in this quarter during 320. While our PCB may not have worked perfectly, the lessons that we learned from this project will extend far into our future career as engineers. We want to give personal thanks to Wallace, Sebastian, and Satya. All three of you were extremely helpful during this project. And that is our presentation for you.